Is probability just coin tossing and picking balls from boxes? How is probability applied in real life? This is the topic of discussion in this video. With this, I welcome you to the Math Exploration Tour. Probability in school. When we learned probability in school, most problems were either related to coin tossing or picking balls from boxes. I have provided two examples of such questions. What is the probability that in the toss of 10 fair coins, there were 3 heads? If 2 balls are drawn from a box with 5 red and 4 green balls, what is the probability that both are green? Probability in the world. Is probability just about coin tossing and picking balls from boxes? Are there any practical applications at all? Indeed, there are plenty of practical applications. Probability is one of the foundations of data science and machine learning, which have gained a lot of popularity these days. Different phenomena, same model. The point is that in probability, the same ideas can be used to model a vast variety of phenomena. This is actually one of the most wonderful facts about the world. Understanding coin tossing and asking several questions related to it helps one to understand hundreds of real life problems with a flavor of uncertainty in them. I must emphasize that this is not an exaggeration. The goal of this video is to emphasize on this point through a couple of examples, one related to coin tossing and the other related to picking balls from boxes. Coin tossing and random walk. Consider a person who moves on a one-dimensional line. You can visualize the number line. He moves right or left by 1 unit. At a particular time, he moves right or left with equal probability. Note the similarity with coin tossing. The above can be modeled using coin tossing. Toss a fair coin. If the result is head, the person moves right. If the result is tail, the person moves left. So now an instance of right-left moves by the person is converted to an instance of a sequence of coin tosses. For instance, if the person moves right-left, right-right, left, then it corresponds to the sequence of coin tosses head-tail, head-head, tail. The question, what is the average value of the time taken for the person to move 10 units to the right of his original position, can be converted to the following question regarding coin tosses. What is the expected or the average value of the number of tosses required for the difference, number of heads minus number of tails, to equal 10? Why is this so? Because at any instant of time, the position of the person is given by a number of rights minus the number of lefts. If the person has moved 3 right and 2 left in some order, then his position must be 1 unit away from the starting position towards the right. Brownian motion. One may think why one should care about a person walking randomly on a line. Replace the person with a particle. Study of the simple random walk enables us to understand the very complicated random zigzag motion of particles in a system. This is called Brownian motion. In fact, the first calculation of the famous Avogadro number was done by using probability. Now let us move on to the second example. Balls from boxes and COVID views. This is called the Polya-Ernst scheme. Consider a box with 20 red balls and 10 green balls. Do the following experiment. Pick a ball at random from the box, put it back, and add another ball of the same color. Repeat. So, if you get a red ball in the first trial, you put that red ball back and add another red ball, so that now you have 21 red balls and 10 green balls. Repeat the experiment. You can ask the following questions. What is the probability that in the 5th trial you get a red ball? What is the probability of getting a red ball in the 3rd trial given that the first 2 balls drawn were red? Second question is an example of conditional probability. Now come to the time of COVID. A tourist comes to India at this time. Think of the red balls as COVID positive and green as COVID negative. What is the probability from the perspective of the tourist that a random person is COVID positive after he sees 10 people? Well, it remains the same as before because he does not have any information on whether the 10 people he has seen are COVID positive or COVID negative. You can compare it to the first question we asked: what is the probability that in the fifth trial you get a red ball? Here also, you did not have any information on what was the color of the balls which were drawn in the first four trials. Now the tourist has seen 10 people infected with COVID. Now, from his perspective, what is the probability that a random person now is COVID positive? Well, it has obviously increased compared to the start. He has seen 10 people infected with COVID, so now he feels that more and more people in India are infected with COVID. Compare it to the second question: what is the probability of getting a red ball in the third trial, given that the first two balls drawn were red? As the first two balls drawn were red, now you have 22 red balls and 10 green balls. So the probability of getting a red ball is 22 by 32, while it was 20 by 30 at the start. Note that 22 by 32 is larger than 20 by 30, so the probability has increased. Thus, there's a similarity between the questions regarding the red and green balls and the questions about about COVID views. We can also change the experiment. Instead of adding one ball of the same color, add three balls of the same color. In the real world case, this indicates that the tourist is more sensitive in nature. On seeing a single person infected with COVID, he worries to that extent. He worries to that extent that he interprets this as three more people having COVID. Conclusion: we understand the importance of two simple experiments: coin tossing and picking balls from boxes. And undoubtedly, this is the reason why they are given so much importance in school probability. While coin tossing helped us to understand random walks, and in turn, Brownian motion, picking balls from boxes, helped us to understand the psychological impact of COVID on the general mass of people. Obviously, these are not the only applications. There are tons of them. The same experiments described here can model several other phenomena. And apart from these, there are different models too. Here we learnt about the Polya-Ern model. Its counterpart is the Friedman-Ern model. Where is that used? Check that out. Thank you. If you liked this video, please do hit the like button. And for more math, please subscribe to the channel. Thank you.